Hello guys and welcome back to my channel. This is another video tutorial continuing from where I stopped last time at Unit 2. If you've watched in my previous video tutorial, you would see I was talking about the different type of parity methods that we can use to make sure that data has arrived correctly at the receiving end, and we talked about how we can use the even and odd parity. Today what we're going to be looking at is how we can actually use parity blocks to detect exactly where an error has occurred when it has occurred during transmission. Like I said last time, using the parity bits, it is a good way to detect if an error has occurred, as you've seen in page 34-35, but the only problem with the parity bits is that it doesn't exactly tell you where the error has occurred once it has been transmitted. And so one method or one way to solve this problem would be to use, of course, the parity blocks. And so that means when a block of data is sent, the number of 1 bits are totaled horizontally and vertically, and this is being counted to make sure that the parity method that is being sent with is maintained. So this method does not only identify the error, but it also says where exactly the error has occurred. Now, if we look at example 2, it says in this example, 9 bytes of data have been transmitted. Agreement has been made that the even parity is supposed to be used. So the method of transmission of parity is even parity. Another byte, which is called a parity byte, has also been sent along with this message. So remember, guys, that whenever data is sent across a network, the computer, of course, does not understand anything in terms of text and letters. It only understands binary, ones and zeros. So that's the reason why when data is sent across a transmission or across a network, it is sent in bytes. And so using this parity block method, of course, the number of bits are totaled horizontally and vertically, as we've seen, but also an additional byte is sent, which is also used to confirm the transmission of data. So this byte that is sent additionally with the message consists entirely of the parity bit that is produced by the vertical parity check, which we're going to see in the table below. The parity byte also indicates the end of the block of data, so it basically tells where the data that is being sent ends. So if you look at this table here, we have a total of 9 bytes of data, and we know that 1 byte of data consists of 8 bits, and of course we have both the rows and the columns. And from the beginning here on the first column, or I would say the second column, you can see that it says parity bit. And so this basic 1, 1, 0, 1, 0, 1, 1, 0, 0, 1 represents the parity bit of each byte in the row. And of course in the column, mostly the row, to be honest, because it does take bytes 1, 2, 3, 4, 5. And in the columns basically just, is again another total number of parity bits. So if we were supposed to find out, let's say this was a message that was sent from computer A to computer B, and the message was broken down into 9 bytes. That means basically each byte represents some part of the message. And we were to find out where exactly the error has occurred, even though an error has occurred, which the computer would be aware of, but where exactly had it occurred during transmission, then the number of parity bits would have to be totaled both horizontally and of course vertically. So let's look at the first byte. Let's look at it horizontally, that is looking at it as a row. We start with the parity bit and we count. Since the agreement that was sent was an even parity, it means the number of ones should be even. So if we count this, we're going to get 1, 2, 3, 4, 5, 6. So this is okay. Byte 1 is okay. If we go again horizontally for byte 2, in terms of rows, we count it, it will be 1, 2, 3, 4. That's also okay. Byte 3 will be 1, 2, 3, 4, 5, 6. That's also fine. Byte 4 will be 1, 2. That's also good because the number of ones are all even. Byte 5 is going to be 1, 2, 3, 4, which is also okay. And then byte 6 is going to be 1, 2, which is also even, and that's also okay. Byte 7 is going to be 1, 2, 3, 4, 5, 6, which is also okay. Byte 8 is going to be 1, 2, 3, where there's a problem, and you can see it's already highlighted in gray color. So this already signals that there is an error that has occurred on this byte horizontally in terms of the row. And if you count for byte 9, you're going to find out that it's also okay because you have just 2 number of parity bits of ones, which means their number of ones is even. And this basically is the final parity byte, which just signifies the end of the message or the end of block of data that is sent across the transmission or during the transmission. So byte 8 is the one with the problem. Now we just have to total the number of bytes, parity bits, that we have vertically as well. So we can exactly determine where the error had occurred. And so that gives us the difference between using parity blocks and parity bits. So if we go on counting vertically the number of parity bits of ones, we go again 1, 2, 3, 4, 5, 6. So this is also okay because it also follows the rule of the even parity. And you notice that I counted with the parity bit from the last parity byte as well. And then you count the second row, or again the third row, which is bit 2. And you go 1, 2, 3, 4, and this is also fine. You count the column for bit 3, and you go 1, 2, 3, 4, and this is also fine. And you count the column for bit 4, and you go 1, 2, 3, 4, 5, 6. And so you get, again, this is fine. This doesn't have any problem. And you go for the bit 5 column, and you get 1, 2, 3, 4, 5. And you notice that there is already a problem here, and there is a problem where it intersects. And so the problem is we're getting 5 parity bits of 1s. And here we got on the byte 8 row, we got 3 parity bits of 1. So that tells you that there is an issue with the byte 8 and bit 5. And of course, to detect how the computer exactly detects where the error had occurred is because basically where there is an intersection of this byte and bit. So if you look here, we had 1, 2, 3, 4. So 5, the fifth parity bit of 1 is basically colliding with the second parity bit of 1 for byte 8. So that tells you that this is where the error has occurred because this is kind of where it intersects. So if there wasn't a 1, perhaps if the 1 was a 0, then we would have a correct transmission because we would just have 1 and then 2, and then we would have 1, 2, 3, 4, and this would not be counted as a 1. So this is the intersection that contains the error. And so as you can see, guys, using the parity blocks, it does, identify where the error had occurred, at least in which particular parity bit, in terms of where the intersection had followed. So here it says a careful study shows that byte 8, which is row 8, has the incorrect parity, and bit 5, which is column 5, has the incorrect parity. So there is an intersection that goes, went wrong there. So perhaps an assumption would be this shouldn't be 1, it should be a 0. But again, there is no 100% assurance of where exactly the change needs to be. Yes, it does say that there is an error that has occurred here where the 1 intersects on byte 8 and bit 5, but it doesn't really say if the 1 needs to be changed to be, the 1 here needs to be changed to a 0, or perhaps another additional 1 could be added on the parity byte or on byte 9. So it just says where the error could have occurred, but it's not 100% assurance of exactly where a change of data or a change of bit should occur so that the correct data should be transmitted. So again, this method is good to basically check and make sure data is transmitted correctly, but it is not 100% reliable. So let's look at more information. It says, first of all, the table shows that an error has occurred during transmission. Secondly, at the intersection of row 8 and column 5, which is basically byte 8 and bit 5. The position of the incorrect bit value which caused the error can be found. So like I said, the position is where this 1 intersects on byte 8 and also for bit 5. Now, so this means that the 8 bytes should have the value of most likely 0. So instead of the 1, most likely this should be 0 instead of 1. And this would correct the column 5 given an even vertical parity. So this byte could therefore be corrected automatically, or an error message would be sent, relayed back to the sender, of course, from the receiving end, so that the block of data could be retransmitted again. But like I mentioned, one final point is that if the 2 bits change value following data transmission, it may be impossible to locate the error using the above method. For example, if there is a change of an extra 1 bit, like I said, so they're using, in the textbook here for the IGCSE, they use the example 1 again. And so the example 1 initially follows from this example here, so where you have 0, 1, 0, 1, 1, 1, 1, 0. And what they're saying is that if, for example, during transmission, 2 of the bits change their values, which, if you recall, guys, what they said was whenever an error had been detected using parity blocks or the location had been found, the receiving end basically sends a message to the sending end so that the data could be retransmitted. And so the data will be retransmitted, but the problem is there might be bits that change value because it's retransmitting the correct set of data, so there would be a change. Now, if 2 bits change their values, then that would mean that it will now become impossible to locate the error, because we will have the ones being even. Of course, for example, if we had 1, 2, 3, 4, 5, and then we have a 6th one here, we have an even parity, but we don't exactly now know where the error had occurred. So that's why it is impossible to locate error. So they give you an example. So this byte, initially the byte was 0101110, but it could have changed while it, when it reached its destination from the sending device to 01111 and 1 at the end. So this, of course, is still correct because it follows the even parity method. But the problem is now it's difficult to be able to locate the error because it does follow the correct even parity method, but it doesn't exactly tell us where the error has occurred, because of that lack of intersection. So maybe you'd have it here, 1, 1, 1, 1, 1, and another 1 here, or even down below. So that's where there's a problem. And it also gives you another example. The probability could be, okay, maybe the 1 didn't change at this 3rd block. Maybe there is actually a change at the 1st, 2nd, 3rd, 4th, 5th block, and 6th block instead of the 1 to change to a 0. So there are many possibilities, and so this tells us that the parity block is not 100% correct method to be able to determine exactly where an error has occurred. If it has occurred, because in the case where the data is being retransmitted from the sending to the receiving end, there might be a change of bits again, and even though it might maintain the parity bit method that was agreed upon the sending and receiving end, whether even or odd, it still does not exactly say, it will not exactly say where the error had occurred. So it says all 3 are clearly incorrect, but they have returned the even parity. So this wouldn't trigger an error message at the receiving end. So clearly that means we would need to look for other methods to find, to be able to get how data could be checked properly. So we're going to be looking at other error checking methods. Now, before we do that, let's look at activity 2.4 and let's try to solve this question. It says the following block of data was received after transmission from a remote computer. Odd parity was being used by both the sender and the receiver. One of the bits have been changed during transmission stage to locate where the error is and suggest the corrected value. So the main key point here is it says that odd parity has been used. So that means you have to total the number of 1 parity bits both vertically and also horizontally. So let's start horizontally and let's count the number of 1 parity bits for byte 1. So we start by counting 1, 2, 3. So this is fine. We count byte 2, 1, 2, 3, 4, 5, 6, 7. So it does maintain the odd parity law, so odd numbers of 1. So that's also okay. We count byte 3. We go 1, 2, 3. So this also does maintain the odd parity bits. And now we go byte 4. We count horizontally 1, 2, 3, 4, and we see that there's already a problem. The number of parity 1 bits that we have here is a total of 4 instead of an odd number. It's an even number. So we have 1, 2, 3, 4. So we immediately highlight this part. Let's continue to look at byte 5. We go 1, 2, 3, 4, 5. So this one maintains odd. We go byte 6. We go 1, 2, 3. So this is also fine. We go byte 7. We go 1, 2, 3. This is also good. By 8, we go 1, so that's fine. And then by 9, we go 1, 2, 3, 4, 5. And that's also okay. The parity byte just signifies the end of the message block. So what we realize is that for byte 4, definitely it does not follow the odd parity that has been agreed by the sending and receiving end, because we see that the number of parity bits of 1 is actually even, not odd. So it doesn't follow the rule. But let us see where the error, let us be able to identify where the error had occurred using the parity block method. So we have totaled the number of parity bits of 1s horizontally. Now let's do it vertically so we can determine where the error had intersected or occurred. So let's go on the column 2, that is the parity bit column. We go 1, 2, 3, 4, and then with the parity bit from the byte is also 5, that's fine. We go to the third column, bit 2, we go 1, 2, 3, 4, 5, that's also good. We go 1, 2, 3, 4, 5, 6, 7, so 7 on bit 3, that's also fine. It does respect the odd parity. For bit 4, we go 1, 2, 3, 4, 5. That's also fine. For bit 5, we go 1, 2, 3, 4, 5. That's also good. For bit 6, we go 1, 2, 3, 4. Now that's a problem. We can already see that we get 4 parity bits of 1 on column bit 6, which means there's already a problem where we're supposed to get odd numbers of ones instead of even numbers. So we highlight this part. Let's check bit 7. We count again 1, 2, 3, 4, 5. So that's also fine. 1, 2, 3. So everything is fine except byte 4 and bit 6. So let's exactly locate where the error has occurred. So when we count again on byte 4, the row section, we go 1, 2, 3. So we notice that we have 3 and we have 4, our fourth one, which goes on bit 7. And if we count here, we go 1, 2, 3, 4. So we need to look at the intersection between byte 4 and bit 6, and we can see it basically intersects at the 0. So which means this 0 probably should have been 1 instead of 0. If it was 1, then for byte 4, we would have 1, 2, 3, 4, 5, which would then respect the odd parity that was agreed upon the sender and the receiving device. And it will also be 1, 2, 3, 4, 5 on the bit 6 column. So to answer this question, the error has occurred on byte 4, bit 6, exactly where the 0 is, because that's where the lines, the row and columns intersect. Okay guys, the next one is the automatic repeat request, and this type of error checking method is basically used to check again if data has been sent correctly. And so what happens is that once data is sent from the senders to the receiver end basically acknowledges that the message has been sent, so an acknowledgement that the message or the data has been sent correctly. And so that's what is called this acknowledgement by the receiving end. And so the receiving end, that is the receiving device, would have to send this acknowledgement within the time lapse that is given for that particular acknowledgement to be sent back to the sending device. If the receiving device does not send this acknowledgement within the time lapse that is has been set for it to send to the sending device, that the message has been received correctly, guys, sorry about that, then it means that the sending end, it will have to automatically resend the message one more time. So I repeat again, what basically happens with this type of error checking method is that the receiving device has to send some sort of acknowledgement, and this would mean that the data has been received correctly, and this acknowledgement has to be sent within a time frame, so that the time does not lapse or pass the timeout. And if the acknowledgement isn't sent back to the sender before the timeout, then the message is automatically resent. Now, some of the questions that usually come from the IGCSE exams have to do with checksums, and this is another method of checking or making sure that data has been transmitted correctly and checking to see that it has on the receiving end. And so it's another way to check if data has been changed or corrupted during transmission. Data is sent in blocks, and so what happens with this checksum, or how it works, is once data is sent in blocks, of course that means in bytes, which is made up of 1s and 0 bits, then an additional value would be added to the end of these blocks of data that is being sent, and that value that is additional is basically the checksum, and it's going to be added at the end of the blocks. So how do we understand the checksum? So to explain how it works, we are going to assume that the checksum of a block of data is equivalent to 1 byte, which basically we know that is 8 bits of data. So if you raise 2 raised to the power of 8, since the computer only understands binary, so we use the 2 raised to the power of 8, which basically means 8 bits equal to 1 byte, we get 255 bits in total. So the value 000 is basically not used when you're trying to calculate the checksum. So the checksum, just to summarize, is an additional value that is basically attached at the end of the blocks of data that is being sent from the sending to the receiving end. And how it works is once the receiving end, that is the receiving device, receives the data, with the checksum at the end, it basically recalculates again by summing up the number of bytes that have been sent with this block of data, and it basically adds the sum and recalculates again the checksum that has been attached to this block of data, and finds out if that particular checksum is the same as the checksum that the receiving device has received. If it is the same, then it means that data has been transmitted without any error. If it is not the same, then it means that an error had occurred while transmitting data, and so it will request for the data to be retransmitted. So here, if the sum of all bytes in the transmitted block of data, so how do we find the checksum? Well, we first have to sum up all of the bytes of the block of data that is transmitted, and we have to see if that sum is less than or equal to 255, because we know that 8 bytes, 8 bits is equivalent to 1 byte. If the checksum is basically less than or equal to 255, that would mean that the checksum is going to be that value. I mean, if the sum for all of the bytes of the block of data that has been transmitted, like you say, hello, my name is Alice. So let's say that's a block of data that will, of course, be converted into binary and transmitted to a sending end, maybe when you're sending an email. So on the receiving end, once that data is received, that data is being transmitted using checksum with a checksum value at the end of the block of data. So it's transmitted in bytes, guys, because you remember data is transmitted in bytes, which means 8 bits or more. And so once the data is received at the receiving end with the checksum value at the end of that block of data, the receiving end would have to look at the checksum value, recalculate, and compare if it's the same. What they're saying here is that if the sum of all bytes of block of data that is being found is less than 255, so the checksum is going to be that value. It will still be the same value, and that will be the value that will be added to the block of data that is going to be sent to the receiving end. However, if the sum is greater than 255, then that would mean you would need to follow the following steps that we're going to be looking at to find the checksum. So if the sum, again, is greater than 255, the way we're going to be finding the checksum is first we have to divide the sum of the bytes of data that is being sent, which is represented with an X value or an X letter. And we're going to divide that sum, which is going to be X, by 256. So we're dividing the sum of the bytes, which is represented as X, by 256. That's the first step to be able to calculate the checksum. The next thing we're going to do is round the answer down. So we're not rounding it up, but we're rounding it down to the nearest whole number, and that's going to be represented as Y. The third step is we're going to find Z, which would mean whatever we got in Y for the second step multiplied by 256. The fourth step is we're going to find the difference between X, which was the original sum of bytes of data that was sent across the network or was transmitted. So we're going to divide that, we're going to subtract that sum from Z. So Z is going to be subtracted from the original sum bytes of data, whatever Z will be. So that's basically going to be step 4. And then step 5, the value that you get after finding the difference between the sum of bytes of data, which is X, and the products of basically the answer that you rounded down by 256, if that value that you get is basically less than 255, remember the rule, then it means the value you got is your checksum. If it is still greater than 255, you're going to have to repeat this step all over again from the beginning. So let's take an example. Let's say, for example, the sum of a particular block of data, which means the sum of the bytes of a particular block of data that was sent to the receiving device, maybe, like I said, hello, my name is Alice. Let's assume that the sum of the bytes of data is 1,185. So the first step, obviously, we're not going to use this value because if you remember the rule is we have to check if it's less than 255, then we can say that's the checksum. But if it's greater than 255, we have to follow these series of steps to find the checksum, and that's what we're going to do. So the first step is to divide it, like we said, by 256. So we divide the sum of the parity of bytes by 256, and we get 4.629. The second step is to round that value to the nearest whole number. So we're rounding it down, guys. It's important you remember. Rounding this down will give us 4. So the value Y is 4. The third step is to multiply 256 by 4 so we can find the value Z, and so we get it as 1,024. The fourth step is to find the difference between the sum of the parity bytes of the original block of data and subtract that from Z that we got. So when we subtract 1,185 minus 1,024, we get 161. And if you compare this value again, you find out that this value is actually less than 255, which means that that is the checksum. So that's the value that's going to be added to the block of data, which of course is this value in total. So to the block of data when sent across the network or during transmission. So when a block of data is about to be transmitted, the checksum for the bytes is first of all calculated. This value is then transmitted with the block of data. At the receiving end, the checksum is recalculated from the block of data received. So this calculated value is then compared to the checksum transmitted. If the values are the same, like I said, then the data will be transmitted without any error. So this is really what happens and how you can understand what really happens during transmission from sender to receiving end, using the method of checksum to make sure that data has arrived or being transmitted without any error. So once the receiving end receives that data, that block of data with the checksum value at the end, it basically recalculates the checksum value and compares to see if it's the same. If it's the same, the receiving end or receiving device then knows that the data has been transmitted without any problems. Of course, if the values are not the same, which means they are different, then a request is sent to retransmit that data. Okay guys, I want us to look at some examples of how we can basically use checksum. So if you look here on activity 2.5, you see that they're telling us to calculate the checksum for the blocks of data with the following byte sums. And you can see that we have this value of 148. I'm just going to write here because it's easier for us to work through. So we have 148, and of course, sorry about that. So of course, 148 is a value that is less than 255. So remember the rule, if it is less than 255, we basically would accept this value as the checksum. So we don't need to calculate anything. This is just going to be the checksum. So we don't need to calculate. So checksum is this value. However, let's look at the next one. The next one is 905. So 905 is definitely not less than 255, but rather greater than 255. In this situation, we will need to calculate the checksum, so we will need to go step by step. So let's do this on a different sheet. So the first step, if you remember, was to divide the sum of the parity bytes, which in this case is 905. We divide this by 256. And so we're going to get a value. So what's the value that we get? If you divide this, you get 3.5. Now the second step was that we needed to round down that number. So if we round down the number 3.5, it's going to be giving us 3. So the value is eventually going to be 3. And remember, this is going to be our y value. So let me write this again. So this is going to be y. Now the third step, if you guys recall, was that we need to multiply that y value by 256 so we can get z. So step 3 is going to be z is equal to our y value, which is basically 3 times 256. And if you multiply this together, you get 768. So 768 is going to be our z value. And then the fourth step is that we need to subtract. So let's look at the fourth step. Fourth step is we need to find the difference between the sum of the bytes and, of course, the product that we just got. So that means x minus y. And if you remember, x is basically this value here, which is 905. So that means 905 minus 768. And if you subtract this, you're going to be getting 137. And so if you compare this value with the original rule, you find out that it is less than 255, so which tells you that this is going to be your checksum value that is going to be added to the end of this block of sum of bytes of data that is being transmitted. So that's how you find the checksum, guys, for anything that is greater than 255, and this usually comes out in IGCSE questions. Okay, so the next thing I would like to do just before we round up this video is I would like us to look at some questions from past paper, which I just got here as an example to show you guys. And if you look at question 5, it says parity checks are often used to check errors that may occur during data transmission. It says a system uses even parity. Tick to show whether the following 3 bytes have been transmitted correctly or incorrectly. So since it tells you what kind of parity has been used, which is even parity, you basically have to count the number of ones and tick if it has been transmitted correctly or incorrectly. So if we do that, we get 1, 2, 3. So this means it has been transmitted incorrectly, of course, because 3 is not an even parity bit of 1, but an odd parity bit of 1. So this is incorrect. Here again, you count 1, 2, 3, 4, 5. And so this also has been transmitted incorrectly. Here you count, you get 1, 2, 3, 4, and so this has been transmitted correctly. So that's how you answer this question. For question B, it says a parity byte is used to identify which bit has been transmitted incorrectly in the block of data. The word flowchart, and remember, the computer doesn't understand flowchart, so like you're translating all of these letters using ASCII characters on your keyboard, of course, into binary so that you transmit that as a byte of data. So that's how you should understand how data is being transmitted, basically. So this word has been transmitted using 9 bytes of data, 1 byte per character. So basically for F, for L, each of these letters have 1 byte that is being transmitted across the network. And the 10th byte, which is going to be represented by the parity byte, it says the following block of data shows all 10 bytes received after transmission. The system uses even parity, and colon 1 is the parity bit. So we know the rule that is agreed by the sending and receiving device, which is even parity. Now we have to check using the law of parity blocks to see and identify where the error has occurred. So we count, or we say we total the number of parity bits of 1 horizontally, and we do that also vertically. Okay, so let's start horizontally. So we count 1, 2, 3, 4. So this is also okay. We go in the second byte by 2, 1, 2, 3, 4. This is also fine. We go by 3, 1, 2, 3, 4, 5, 6. This is also fine. We go by 4, 1, 2, 3, 4, 5, 6. This is also fine. We go by 5, 1, 2, 3, 4. This is also fine. We go by 6, 1, 2. This is also great. It's also okay. We go by 7. We get 1, 2, 3. We immediately know that there's a problem here. So byte 7. So let's mark that with another text color. So byte 7. There is an error that must have occurred here on this line, definitely, because we count the number of ones to be 3, which is odd, not even. So we know that this part, basically, there must have been an error during transmission. So we need to find, of course, the corresponding colon to know where the intersection or where the error had occurred. So if we continue counting on byte 8, the number of parity bits of 1, we go 1, 2, 3, 4. This is also fine. It maintains the rule. And the last byte, which is 9, 1, 2, 3, 4, and this is fine. So we figure that it's byte 7 that has a problem. Now we have to total the number of 1 parity bits vertically. So let's count 1, 2, 3, 4, 5, and then we have 6, and then we have 7. So this is also fine. And then, oh, sorry, we have 8. So this is also great. So this is fine. We do the same thing for column 2. Column 2, we really don't have any ones. Column 3, you do the same. You count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is also fine. You do the same thing for column 4. You go 1, 2, 3, 4. This is also good. You do the same thing for column 5. So this one is fine here. You count them again. 1, 2, and then you have 3, and you have 4. So this is also good. You do the same for column 6. 1, 2, 3, 4, 5, 6, 7. And you know immediately that there is a problem because we're getting, again, an odd parity total of, an odd parity bits of 1s instead of an even because we get 7 1s. Let's count for bits column 7 and see if it's going to be different, of course. 1, 2, 3, 4, 5, 6. So you see that this maintains the rule of even parity. And let's do for 8. We get 1, 2, 3, 4. So this is also good. So the problem is where we have byte 7 and we have, of course, colon 7, if I'm not mistaken. So let's just count to make sure again, because 1, 2, 3, 4, 5, 6. Oh no, not colon 7, it's colon 6 then. 1, 2, 3, 4, 5, 6, 7. Yes, colon 6, because we get 7 parity bits of 1s instead of an even parity bit. So the error has occurred between byte 7 and, of course, so byte number 7 and then colon 6. And exactly where it had occurred was where the 2 bytes and bits and colons, intersect, which is exactly here on this 1 value. So perhaps this should have been a 0 instead of a 1. If it was a 0, then you get 1, 2, 3, 4, and then you get 5, 6. So it's going to be even on column 6, and it's going to be even on byte 7 because you get only 1 and you get 2. So the problem must have occurred here. So we identify the error, and of course, the byte number is 7 where it had occurred and is 6 where the colon intersection had also occurred. So this is an example of the past paper questions, guys, where you can see this kind of questions being asked for the use of checksums and parity bits and blocks. The last thing we're going to see before I end this video is the echo check. And so this type of check basically is when a data is sent from, blocks of data is being sent from the sending end to the receiving end. What really happens is once it's reached the receiving end, a copy of that data that has reached the receiving end is being sent back again to the sending end, so that the sending end or the sending computer can then compare the two sets of data and see if the transmission of data has been, successful without any errors by making sure they're the same. Of course, if it had not been successful, then it will have to retransmit. So as you would see, that this is not a very efficient and reliable method of, again, determining where the error has occurred with data that has been transmitted, because if it might be possible when the sending end does send the block of data to the receiving end and that copy is sent back to the sending end, even if there had been an error that occurred, the sending end doesn't really know where the error had occurred, whether it was when the data was being sent or when it was being resent back. So it is not a very efficient method of determining where data has occurred, where an error of data transmission had occurred. However, if there are no errors that hadn't occurred, of course, if the data that is being resent to the sending end is the same as what was sent originally, then it is also considered as a method of checking data properly to see it has arrived intact. So we're going to stop here, guys, at our video tutorial for Unit 2, and next time when we come, we will continue from 2.4. This is the last point we will stop, and check out my next videos. That is going to be for the IGCSE Past Paper 2 questions from last time when I did show the program and I mentioned I was going to do the questions as well. And I will also be doing a third video tutorial that will be looking at new IGCSE Past Paper questions and how to create the program for that. All right, guys, see you next time. Take care, everyone.